Hello everyone and welcome back. This is chapter 6.3 where we'll be discussing trigonometric functions at any angle. Now recall in the last section we found sine, cosine, and tangent of these angles here. And notice first off they're in radians. So just to remind us, pi over 6 is 30 degrees, pi over 4 is 45 degrees, and pi over 3 is 60 degrees. All right. So now what we want to do is we want to extend this idea of what sine, cosine, and tangent were as far as right triangles were concerned, and try to extend that notion for any angle for that matter. And the best place to start, I believe, is, this circle of radius r centered at the origin. So it'll have this equation, x squared plus y squared is equal to r squared. And there's a nice connection that we'll see in a second. But before we get there, let's kind of imagine that we have a point on this circle. Let's say it's here in the second quadrant. Doesn't have to be, could have been any other quadrant. I don't want to talk about the first quadrant because, you'll see what happens shortly. So if we create the radius from that point to the center, so just the straight line distance, straight line like this, and then we consider the radius from the positive x-axis in a counterclockwise fashion and call that angle theta, then we have an angle that we actually would never consider for sine, cosine, or tangent, because if you consider right triangle angles, the angle is always going to be acute, and this is an obtuse angle. And it would get even worse, actually, if we were in the third or fourth quadrant, of course. So now we ask, what is the natural way of extending the definitions of sine, cosine, and tangent? And here's the idea I want to give you. If you actually make a perpendicular down to the x-axis, kind of as you would in the first quadrant actually, you'll get a right triangle. The only difference though is that since this point is of course x comma y, then this will be x, this will be y. So just to draw this triangle a little more zoomed in over here, I guess, we have this right triangle. The only real difference is, this angle is not the angle we're looking at. In fact, this angle actually has a name. The book calls it theta prime. Other books call it theta bar, like this. But I'll use theta prime because it's consistent with the book I'm using for this class. But in any event, it's called the reference angle. I'll just abbreviate that REF for reference angle. And the reference angle can be found in multiple different ways depending on what quadrant you're in. In this case, we can see that it's just 180 minus the angle is the reference angle. In the second quadrant, that is. But the biggest thing I want to emphasize on is that what is the distance of the base of this triangle? What is the hypotenuse of this triangle? And what is the vertical side of this triangle? If we believe this point, then this distance is just x. Similarly, the vertical distance is y. And, of course, this distance is going to be the radius. Right, so the good news here is that the radius will always be positive because it's a positive radius, of course. So radius is given to be positive. Y could be negative or positive depending on what quadrant you're in. In this case, y is actually positive. But here, x is actually negative because in the second quadrant, this point would have a negative x value and a positive y value. But we kind of see that this extends the idea of sine, cosine, and tangent beyond just the first quadrant, because now we'll consider angles that are larger. The only issue is that we get negatives into the mix. But anyways, we can still construct somewhat a triangle, but now we'll have negative sides possibly involved. But still, if you take a look at this and consider this right triangle, this is a perfect opportunity for sine, cosine, and tangent to jump into place. Even though it'll be of theta prime, not of theta, if we consider the negatives, then that'll be the trig function of theta itself. So sine of theta, cosine of theta, and tangent of theta will just be these values if you consider them being, with their signs. So in this case, cosine, I guess let's talk about sine first. Sine is opposite over hypotenuse, so that's going to be y over r. X over r will be cosine, and then y over x would be, if that makes sense, it's going to be opposite over adjacent for tangent, and for cosine, that's adjacent over hypotenuse. But again, the details on theta prime we have yet to discuss. We'll discuss that in a second. But for right now, I just wanted to give us this idea here that this is our new notion of trig functions beyond the first quadrant. Because of course, if you look at points that are in the first quadrant and connect those to the origin of the circle, then you will get triangles, and in this case I drew 3 triangles. Now they could represent any angle, but I actually want them in this case to represent particular angles that I have listed above: pi over 3, pi over 4, and pi over 6. And we can actually find sine, cosine, and tangent of those, and they're just these actually. But again, how we would do that beyond the first quadrant may not have seemed very obvious, but now we have the understanding of how we do it. Just the same way, just consider x and y values that could possibly be positive depending what point what quadrant, I guess, your point lands in. The last thing I wanted to say before we move on, though, is recall this. This is x squared plus y squared is equal to r squared. Well, it's kind of cool. If you divide everything by r squared, you get this. X squared over r squared plus y squared over r squared, which I'm writing like this, equals r squared over r squared, which is 1. And what do you notice about x over r and y over r? They are exactly cosine and sine, respectively. And the signs don't matter, because when you square, regardless if the fraction will end up being positive or negative at the end, when you square it, you'll get positive anyways. So in fact, we can see that this new extension of sine and cosine into angles beyond the first quadrant make a whole lot of sense. So now we'll talk about reference angles in more detail. All right, so here we'll discuss more details of the reference angle theta prime, like I mentioned before. So this dash notation is pronounced prime in mathematics. And here we say that theta prime is just the acute angle formed in between the x-axis and the terminal side of the angle theta. So in this case, if you consider this angle where we land in the second quadrant, this angle here in between the terminal side and the x-axis would be theta prime. So that's theta prime here. And below I'll actually discuss what theta prime is, but for right now let's just kind of get the idea of understanding what the angle is, or at least where it's located anyways. Here, where is theta prime? Well, here the angle will land us in the third quadrant, the terminal side that is will land in the third quadrant at that angle. But between the x-axis and this terminal side, the only angle we can form that's acute is this one here. So this is theta prime. Okay, here, when we're landing in the fourth quadrant, this would be theta prime. The only case I don't have really represented here is the first quadrant. And as it turns out, in the first quadrant, theta is already acute. So in that case, theta prime would just be itself, which I'll label that shortly in this section. But for right now, let's continue with these examples. So let's see. If this angle is 120 and the whole angle between half a rotation is 180, then this would have to be, 180 minus 120, so that would be 60 degrees. Okay, there's a similar idea happening here, but it's not quite the same. So notice 200 degrees is beyond 180, but this reference angle would just be the difference between that and 180, how far it's beyond 180 actually. So this reference angle in this case, theta prime, is 200 minus 180 degrees, which is 20 degrees. And notice we indeed are getting acute angles. And of course, acute just means in between 0 and 90, if you didn't know already. And now for this one, well, let's kind of think about what happens in degrees before we get into radians, because I know that idea can be a little daunting for us, but let's just kind of hear me out here. So again, here we have a very similar idea to what we had for this case here. Here, this was the completion of 180 degrees, and theta prime here completed that half rotation. Here, it's not 180, but now it's a full rotation of 360 degrees. So here, the angle will land us in the fourth quadrant, but the reference angle theta prime, in this case, will actually complete one full rotation of 360 degrees, so that means this will be 360 degrees minus this angle here. The only thing is it's in radians. So let's recall, 360 degrees is how many radians? That's right, it's 2 pi radians. So that means this answer here is going to be the difference between one full rotation and our angle, which is 5 pi over 3. So it's going to be 2 pi, let me write it here actually. 2 pi minus 5 pi over 3. If you find a common denominator, you can actually write 2 as 6 pi over 3. Right, that kind of makes sense because 6 pi over 3 reduces to 2 pi over 3. And then subtracting these, we just get pi over 3, which by the way is the same as 60 degrees. And that makes a lot of sense if you convert this into degrees and do it the other way around. And there we go. All right, so now I'm going to discuss in general kind of what we've been doing here. And it's not very hard to justify because I already just justified it actually. In fact, no matter what these angles are, as long as they land you in quadrants 2, 3, and 4, you do exactly what I said. So remember that I said that in quadrant 1, theta bar, or theta prime, the reference angle, is just theta itself. In quadrant 2, it's the difference between 180 degrees and that angle. So let me just write 180 degrees minus theta. Because again, theta is the original full angle. Theta prime is the reference angle, which is acute, but theta isn't necessarily acute. Okay, here, what was this? Well, here this is when we went a little beyond 180, and it's the difference between the complete angle and 180 in the opposite way that we did for quadrant 2. So here this is theta minus 180 because our angle is now a little bit beyond 180. Okay, so that should make a lot of sense. Great, so now for this one, again, this is similar to quadrant 2 in the sense that this completed one rotation, which was 360 degrees. So this was 360 degrees minus theta. And of course, we could write these in radians. So in radians, this is pi minus theta, theta minus pi, and finally 2 pi minus theta. Okay, perfect. So now we have a really great understanding, hopefully, of how to calculate and find the reference angle. Now, exactly how the reference angle will affect our calculation of sine, cosine, and tangent for a particular angle, we have yet to see, but we'll take a look at that right now, in fact. All right, so just jumping right into it, let's see if we can evaluate sine, cosine, and tangent of these particular values here. And of course, we're going to use a circle to try to figure out what's going on. And I'm going to use a unit circle, so the radius is going to be 1. And of course, when your radius is 1, it just makes the values a lot easier to find, because since the radius is 1 now, well, then x over 1, y over 1, those are just x and y themselves. So in fact, sine and cosine are really just following points on the unit circle, which is kind of nice when you think of it like that. The only issue is that, well, when you go 120 degrees for here, you'll end at this point in the second quadrant. And how I know that, of course, is because here this represents 90 degrees at the positive y-axis right there. And 120 is just a little bit beyond that, but not quite 180, because that would be, well, here in the negative x-axis. Good. So that angle makes sense. But now exactly what the point is, well, we don't know the x and y values of this point, do we? Not right away we don't, but by reflection, in other words, by symmetry of circles, what we can do is we can say that this will kind of be the same point over here on this side of the circle. Now, it won't necessarily be the exact same point, but it'll be the same as far as the y values go, and the x values by symmetry will just be opposites. So, there we go. And the nice thing here is that we know this angle. Well, do we know that angle? Actually, we do, because notice it's just the same as this angle, and this angle is, aha, that's just our reference angle, theta bar. So, good. So that means all we really need to do is find out what the reference angle is, and then find, well, the x and y values of that point, and then reflect it over. And notice these x and y's aren't necessarily the same as these x and y's, but they're fairly similar. In fact, if we just kind of look here for a second. So if the reference angle is, well, again, we already saw how to find the reference angle in the second quadrant. It's 180 minus 20, so that's going to be 60 degrees. And let's see. If the radius is 1 on the unit circle, then we actually know what these are. In fact, if you can kind of consider sine and cosine of 60, what was sine of 60? Sine of 60 was, well, I guess it was radical 3 over 2. So that's the same as radical 3 over 2 over 1. Cosine of 60 is 1 over 2. So that would be 1 over 2 over 1. Meaning that the x value of this point is going to be 1/2. And the y value of this point is going to be radical 3 over 2. Now what that will reflect to on the other side will have, well, the same y value, radical 3 over 2. So let me just erase and replace with that. But the x value now will be the negative version of that number 1/2, which in this case, of course, is negative 1/2. So let me just move this labeling over here. Okay, got a little messy, but that's fine. All right, so perfect. So now we have the points and we have the radius is 1 in this case. So we know that the definition of sine that we're working with is, well, if you remember, it was y over the radius because we have this value here. So it's going to be this distance divided by the radius. Since that distance is just y, it's going to be radical 3 over 2 over 1, which is just radical 3 over 2. So as it turns out, we didn't even need that negative 1/2. But if we were finding cosine of 120, then we would. And in fact, we'll talk a little bit more about really what's going on and how to quickly determine these. In fact, maybe I'll just try to give you the idea right now. So let's just kind of think for a second. So 5 pi over 4, remember the over 4s are just 45s. So here, this would represent, just so it's not super cluttered, I'm going to erase this and draw a new unit circle for us. So here we have a better image fitting for number 2 here. This, of course, is the unit circle with particular angles in mind, the pi over 4 multiples. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So 5 pi over 4, notice, lands us in the third quadrant, where our x value is negative and our y value will also be negative. Now, instead of doing it the weird way I did for the first part, I really just did that so we can get an understanding of how we can find the value based on the definition that we saw for sine, cosine, and tangent alone. But the better way of doing it really is just creating a triangle with the reference angle. That's really the key thing we want to develop. So if you look here, our reference angle theta prime is, well, it's just going to be pi over 4 actually. And that's not too hard to see because, again, this half rotation here is just pi radians. And the difference between 5 pi over 4 and pi, well, pi is 4 pi over 4. So notice 5 pi over 4 minus pi over 4, or 4 pi over 4, is just 1 pi over 4. So here, theta prime is pi over 4. And even better, I'm going to do this for us. I'm going to draw this triangle in that same orientation. I'm going to try to blow it up a bit so it's easier on the eyes. There we go. It looks okay. And the angle here is pi over 4. That is our reference angle. Now, we are going to keep the same signs of the sides though. And notice, since this is a unit circle, of course, what do you think the radius is? Everyone better be shouting out 1. Good, no surprise there. And the x value, yes, it's negative because we're in the third quadrant. X values are negative in the third quadrant. So we'll figure out what this is in a moment. And similarly here, well, this is also negative actually. And there are a few ways you can actually find out what these are, but in reality, all they really are just, well, of course they're negative, like I was saying, but the absolute values, the non-negative parts of the numbers, are just radical 2 over 2. So I may have hyped it up too much, but there we go, that's what those values are. Now, how do we know this? Well, we know this because we actually know what sine and cosine of pi over 4 is. Sine of pi over 4 is radical 2 over 1, radical 2 over 2 over 1, and cosine of pi over 4 is radical 2 over 2 over 1. Now notice I'm just saying them without the signs because that's what we're used to, but now since we have the signs involved, then that won't correspond to sine and cosine of pi over 4. That's just the reference angle to give us an idea of what these values are. But instead, it's to give us an idea of what it will be including the signs. So now for cosine, well, cosine is this side over the hypotenuse. So it's going to be negative radical 2 over 2. Okay, so that kind of helps, I think. But again, we'll try to get better at this idea. Now, as it turns out for tangent of pi, this one's a little tricky. If we try to create a right triangle, it's not really going to work too well. In fact, just to show you, at pi, this is the point on the unit circle. And notice, well, it's just a straight line. There's no triangle you can create from this. In fact, one way of thinking of this is a triangle will look something like this. It will have a horizontal distance of -1 because it's 1 in the negative direction, and it has a vertical distance of 0 because, well, it has no height. Also notice this point is literally the point -1, 0. So its x value naturally is this distance and its y value is naturally this distance. And of course the radius is always 1, on the unit circle anyways. Now again, since tangent is opposite over adjacent, this is going to be 0 over -1, which is just 0. And that should make a lot of sense because, again, what we saw for the extension of the definition of tangent for any angle, it's just y over x, which would be 0 over -1 anyways. So this was the answer for number 2, and this is the answer for 3. All right, so now I'm going to try my best to combine these two ideas to just get a better handle on how to find these particular values of sine, cosine, and tangent for any angle on the unit circle. All right, so this is one of the biggest ideas and the most pivotal points in this section is where we start to get a better idea of how to evaluate trig functions of particular angles that are beyond the first quadrant. So here I say since that sine, cosine, and tangent are defined to be y over r, x over r, and y over x respectively, well, it wouldn't be a bad idea to consider the unit circle, that is when r is equal to 1, because that makes sine and cosine easier to find, like I mentioned previously. Also, if you take a look at the quadrants, well, we'll notice something kind of interesting that happens is we don't actually care what the numbers are right now. Let's just kind of look at what the signs are, because we saw that the signs come into play a lot, and we actually will get similar numbers to what we got in the first quadrant, but now with plus or minus kind of depending, and it's hard to figure out which one is which. But here we'll get a really, really good handle on that. So now in the first quadrant, a point is positive, so its x value and y values are positive. In the second quadrant, its x values are positive, but its y values are, well, actually, I'm sorry, its x values are negative, but its y values are positive, is what I meant to say. So that's negative, positive. Perfect, like that. And now in the third quadrant, here we go, the x values are negative and the y values are also negative. So negative, comma, negative. So here I'm just kind of determining the sign. And what about in the fourth quadrant? Well, its x value is positive because that projects to the x-axis, positive x-axis. But the point projects to the negative y-axis, so it's positive, comma, negative. And remember, these points are x, comma, y. R is 1, so we don't really care about r in this case. In fact, in general, r is positive anyways. So in reality, all we need to do is look at either y or x to find out if sine or cosine will be positive or negative. So since sine is y over r, and since y is positive in the first and second quadrant, that means sine is going to be positive in those quadrants and negative in the others. Similarly for cosine, since cosine is x over r, well, cosine will be positive when x is positive and negative when x is negative. So it'll be positive in the first and fourth quadrants. That's when x is positive. There we go. And negative in the second and third quadrants. What about tangent? Well, tangent is y over x, so it's positive when they're both the same. So positive over positive is a positive, so it's positive in the first quadrant. Negative over negative is actually also a positive number, so tangent will be positive in the third quadrant, but then negative over positive, or I guess positive over negative, because y over x, would be negative numbers, so it's negative in the second quadrant, and negative over positive is going to be a negative number, which again is negative, so tangent will be negative in the fourth quadrant. There was a lot of rambling, but hopefully we followed the argument there. And now this is a kind of shorthand way people generally remember this. A stands for all. So what this really says is that all trig functions, even the weirdo ones, the reciprocal ones, actually, believe it or not, are going to be positive. So this is a acronym for basically remembering where each thing is positive. So all trig functions are positive in the first quadrant. Only sine is positive in the second quadrant, meaning that cosine and tangent will be negative in this quadrant. Tangent will be, so I guess I can abbreviate. So tangent will be positive in the third quadrant and only tangent, so sine and cosine are negative in this quadrant. And you can verify that based on the reasoning I gave you just now. And here in the fourth quadrant, only cosine of these three is positive, so the other ones are negative. And a nice way of remembering the acronym here, ASTC, is by the phrase, all students take calculus. And chances are, if you're watching this video, you're more than likely on the track to taking calculus. So I don't know if this is necessarily true in general, but it's true for you, probably. And here is a beautiful, beautiful, beautiful consequence that hopefully everyone remembers, even after taking this course. Any trig function, whether it's sine, cosine, tangent, even the weird ones, like we'll see cosecant in a moment, of any angle is plus or minus that same trig function of the reference angle. Now, the plus or minus symbol here represents a possible sign change depending on which quadrant it is. So basically, it depends on this acronym here. So this depends on all students take calculus. Great. So all we need to do is figure out what the trig function is and then what quadrant we're in, and that'll actually determine, based on this here, what sign we use. So for instance, if it was sine and if theta was in the second quadrant, well, let's take a look here. In the second quadrant, sine is positive, so it'll be a positive. If it was in the third quadrant and it was cosine, well, only tangent is positive in the third quadrant, so cosine would by default be negative. So it's going to be negative cosine of the reference angle. So let's see if we can utilize that. To be quite honest, again, this is a really subtle idea, but it will make things go a lot faster. So let's see if we understand. So 2 pi over 3. So we know it's going to be cosine of, we need to understand what the reference angle is. Now, all of these are in radians. It kind of made it a little hard on us. But 2 pi over 3 is actually in the second quadrant. So it's over here. And remember, we want to complete 180 degrees, which is pi. So 1 over 3 plus 2 pi over 3 will be 1. So 1 pi over 3 is what I meant to say. So the reference angle really is pi over 3. So if you add these, you get 3 pi over 3, which is just pi, which is the full 180 rotation. Okay, good. Now, since it's in the second quadrant, is cosine positive or negative in the second quadrant? Well, according to this, only sine is positive in the second quadrant, so by default, cosine would have to be negative. Perfect. And this is actually one of the values I gave you at the very beginning of this video. Cosine of pi over 3 was 1/2. So this is going to be negative 1/2. Now, again, I did that kind of quick, but how was I able to remember that value that I wrote a while back? Well, if you take a look at them, there's, only a few of you will actually take time to actually remember these things and devote time to do that. You don't necessarily have to. There's a trick I want to show you that'll actually help you figure it out that I'm using in my mind to just come up with that on the fly, but we'll discuss that soon after completing these examples. So now tangent of 7 pi over 4. Well, let's see. So we kind of saw this earlier. So pi over 4 would be here. This would be 3 pi over 4. Then this would be 5 pi over 4. This is 7 pi over 4. So that's in the fourth quadrant. So it's going to be tangent of, well, in the fourth quadrant, how do we find the reference angle? If this angle right here is 7 pi over 4, then we need to complete 2 pi. So notice if you add pi over 4 to 7 pi over 4, well, you get 8 pi over 4, which is indeed 2 pi. So this is pi over 4. And is tangent positive or negative in the fourth quadrant? Well, in the fourth quadrant, only cosine is positive, so tangent would have to be negative then. And again, by the previous values I gave you at the very beginning of this video, tangent of pi over 4 was 1, so this will then be negative 1. Okay, now for cosecant. So cosecant's funny, but remember it's the reciprocal of sine. So we're really just going to consider sine, and then from this we'll reciprocate it to get cosecant. So to find this, let me just say we want to find sine first. So let's just consider sine of 5 pi over 3. 5 pi over 3 will actually be in the fourth quadrant. And a really quick way, I keep showing you shortcuts here, but a quick way of figuring out what quadrant it's in is by counting by over whatever this is. So, and looking for non-cancellations. So this is an over 3, so there's pi over 3 in the first quadrant, 2 pi over 3 in the second quadrant, 3 pi over 3 reduces, so we don't consider that one. 4 pi over 3 doesn't reduce, that's in the third quadrant. 5 pi over 3 would then be here in the fourth quadrant, and notice 6 pi over 3 reduces, so we don't consider that one, and that actually is 2 pi, which will lead us back to one full rotation. So that's a nice way of figuring out what quadrant you're in, just counting over 3's until you land at this one, ignoring all fractions that reduce. So this is in the fourth quadrant. Sine is negative in the fourth quadrant because only cosine is positive. So this is a negative sine of, and there's an even better shortcut, I guess, to find the reference angle when it's in radians. And this is the beauty of radians. You just ignore the numerator. That's all you do for these special angles anyways. So this is pi over 3. And notice that's exactly what happened here. If you ignore the numerator, the reference angle was pi over 3, and here it was pi over 4. And that'll always work for all the special angles we've been taking a look at so far. Okay. So, so sine of pi over 3 from the previous values we saw was radical 3 over 2. So this is negative radical 3 over 2. Perfect. So that means if you reciprocate that, you'll get negative 2 over radical 3. And of course, if you want to rationalize, you can multiply top and bottom by the square root of 3 to get negative 2 radical 3 over 3. So let me write it like this. Perfect. Let me center that a little better. Awesome. Okay, so now we still have a little bit of unfinished business to do. I have to show you sine, cosine, and tangent of other special angles, kind of like we saw for tangent of pi that was 0. We'll take a look at some that will result in 0, and even one that's a little funnier than that. And then I'll also show you that other shortcut I was telling you to figure out what values of sine and cosine are of angles in the first quadrant, kind of on the fly like I did previously. Right, so here, like I said, I'd be showing you sine, cosine, and tangent of particular values that we quite haven't seen yet. We saw tangent of pi. I'll explain what these values have in common, and then after that, I'll of course show you this trick for finding sine and cosine actually of any value in the first quadrant pretty quickly. There's a nice pattern that actually emerges. But anyways, so if you haven't realized already, what 0, pi over 2, pi 3, pi over 2, and 2 pi all have in common is they're just basically the right angles on the unit circle. In other words, they're the points that attach to a coordinate axis. So in other words, it's this. So we have 0 radians, pi over 2 radians, this would be pi radians, this is 3 pi over 2 radians, and then we get back to 2 pi. And again, the equality just means that they are coterminal, not necessarily equal. All right, and as it turns out, any coterminal angle will have the same cosine, sine, and tangent values. That I haven't emphasized on, but that actually is true. And it makes sense because they'll correspond to the same point on the circle, and by the definition we saw for those trig functions, they only have to do with that point on the circle itself. So there's no real difference really, as long as you land at the same point, and coterminal angles will do that all the time. Anyways, so getting back to this, remember that sine is, well, if it's a unit circle, sine is always y over r, cosine is always x over r, tangent is y over x. So sine is the y value of the point, cosine is the x value of the point, tangent is the y value divided by the x value. That's what we agreed upon. We've been using that actually. So here, for 0, what is the y value? Remember, sine is the y value. Sine is the y value of this point is 0, then 1, then 0, then negative 1, and then back to 0. So in fact, that's what these values are. Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 3 is negative 1, and sine of 2 pi is back to sine of 0, which is 0. So these are the same. In fact, similarly, these will be the same, and these will of course be equal as well, because, well, of course, 0 and 2 pi are coterminal angles, like I mentioned previously. So now can we figure out what these remaining values are? Well, yeah, cosine will be easy. Cosine, again, is the x value of the point on a unit circle. So in order, 0, pi over 2, pi, and 3 pi over 2, we'll get these values, 1, 0, negative 1, and 0, and I'm just pointing at the x values of those points. So let me write it in black here. We get 1, that's the x value. The x value here is 0, then negative 1, then 0 again, and then back to positive 1 for the x values of the points. Okay, now for tangent, things get a little funny. We need to divide y by x. So this is going to be 0 over 1, which is 0. Pi over 2, this is where it gets funny right away. We get 1 over 0, which is actually undefined. And that's actually true. It's kind of sad. So I'll write a sad face. But tangent of pi over 2, believe it or not, is an undefined value. So we'll leave it at that for right now. Tangent of pi is 0 over negative 1, so that's 0. Tangent of 3 pi over 2 is going to be negative 1 over 0, which again is undefined. Again, makes me sad. And tangent of 2 pi is the same as tangent of 0, which is just 0 itself. Awesome. Now, a really nice thing to remember is we had that quotient identity for tangent. Tangent is sine over cosine. And notice when you just divide these values, it's literally just dividing the y value by the x value, because sine is the y value of the point on the unit circle, and cosine is the x value of the point on the unit circle. Good. Now for the moment you've all been waiting for, the trick. So here's the trick to remember sine of any angle in the first quadrant, and then of course cosine, and then if you divide sine by cosine, you can then get tangent. So let's see if we can follow. So the first thing I'm going to do is I'm going to set this up by writing radical 2 over 2. Well, maybe not radical 2 over 2, but I'll write radical over 2. Let's start there. Okay. So radical over 2, radical over 2, radical over 2, radical over 2, radical over 2. Now this is just some pretty, I guess pretty kind of coincidental pattern that occurs with sine of these values. Now notice these values are just the values starting from 0 to 90 degrees, which is pi over 2, in the first quadrant. So that's just these 5 values. In order, 0, pi over 6, pi over 4, pi over 3, and pi over 2, so I've just written them like this. Now, the pattern is the following. Inside the radical will be 0, 1, 2, 3, and 4. And that's it. That's kind of what I remembered. And this is, of course, 0. This is 1/2. This is still radical 2 over 2, not changed. This is also unchanged, radical 3 over 2. Radical 4 is 2, and 2 over 2 is 1. And notice, it even works for these ones that we hadn't really seen until this point. Sine of 0 is indeed 0. Sine of pi over 2 is indeed 1. So nice. But now, how do we use this to find cosine? Well, remember, cosine is the cofunction of sine. So if you take 90 minus these angles, you'll actually just get them listed in reverse order. So meaning what we can do is to find cosine of these angles, we'll just write this. We'll write cosine of, for each one of these. So I encourage you to do this on your own, because the more you do this, the more you'll start to remember these things. And it'll be more intuitive as to why they fall in this order. And now for the angles here, I'm just going to reverse that list for cosine. So pi over 2 will come first, then pi over 3, then pi over 4. Notice they're the same, right? It's what we kind of been seeing. And, right, so then it would be pi over 6, and then 0. Great. And if you wanted to find tangent, well, let's see if we can do that real quick. So we have tangent of, I guess we can just write them in the same order. 0, pi over 6, pi over 4, pi over 3, and pi over 2 finally. Now remember, tangent is sine over cosine. So we'll have to divide sine by cosine of that same angle. So sine of 0 over cosine of 0, well, that's just 0 over 1, so that's 0. Tangent of pi over 6, sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. So this is this multiplied by the reciprocal of this, because when you divide fractions, you multiply the top by the reciprocal of the bottom. So we'll get, if you reciprocate this, the 2's cancel, you get 1 over radical 3, which if you rationalize, of course, is the same as radical 3 over 3. Tangent of pi over 4, this one's where it gets interesting, because since they're the same, they're both radical 2 over 2, and since tangent is sine over cosine, any number divided by itself is 1, so this is 1. Perfect. Tangent of pi over 3 is this value for sine, radical 3 over 2, multiplied by the reciprocal of cosine of pi over 3, which is 1 over 2. When you reciprocate this and multiply here, the 2's cancel, and you just get radical 3. And tangent of pi over 2 finally is sine of pi over 2, 1, over cosine of pi over 2, which is 0, and that is undefined. Nice. And then I'll leave it up to you to actually find the reciprocals of these, so in other words, cosecant, secant, and cotangent. And if you want to go beyond this, you can of course find them at all of the corresponding angles in the other quadrants just by using that idea I gave you previously, where you consider the sign based on the acronym All Students Take Calculus, along with the reference angle calculation, basically. Now I want to do one more example, and this is going to be where we put everything together finally, and hopefully we have a lot of fun with it. Let's take a look at that right now. Alright, so now finally for this example where we start to put everything together, we are given two things. We're given that cosine of theta is 8 over 17, and the tangent of theta is less than 0. Now we did a problem like this in the last section, but we didn't have an additional constraint here. Now of course in this case the additional constraint is for us to figure out what quadrant we're in, and then we can apply that same idea we did for that section, for those examples that is. So let's kind of figure out what's going on here. So as far as what quadrant we're in, well, remember the acronym All Students Take Calculus. We know that cosine is positive, so that means it's either in the first quadrant or in the fourth quadrant, because that's where cosine is positive only. But since tangent is 0, it can't be here because tangent is positive here, because all of them are positive here. So that means it has to be in the fourth quadrant. Perfect. So let me erase these. You can think about that a little more. But yeah, so it ends up being in the fourth quadrant. Perfect. So if theta is in the fourth quadrant, then we have this image going on here for theta. And what I want to do is I want to focus in on this triangle here, but we'll just consider the fact that this will be a negative value for y. So y is going to be negative. The x value will be positive. So that makes sense because again, cosine is x over r. And again, on the unit circle, it's 1. But in this case, I'm going to actually take advantage of this quotient here. But we'll go from there, actually. So let's see. So just writing this triangle over here. Well, cosine of... So this is, I guess, the reference angle, really. But if we consider cosine of theta is 8 over 17. And that would be, well, adjacent over hypotenuse. Now, can we find the remaining side of the triangle? Yes, we can using Pythagorean theorem. So that's going to be, well, there's actually a nice way of doing it, because remember that we're doing 8 squared plus this squared is equal to 17 squared. So that means our question mark value is actually just going to be the square root of the hypotenuse squared minus the other one squared. Since the hypotenuse is always what you amount to, you would be subtracting in this case from the hypotenuse. Now 17 squared I know will be 289. So this is 289 minus 64. And 289 minus 64 actually is 225. Which is nice because the square root of 225 just gives you 15. Perfect. So let me erase this so it's a little less cluttered. So we have 15. And notice it's technically a negative 15. So that way we don't have to think about too much about what the signs are. We'll just treat it as a negative value and then take sine, cosine, tangent, and the other ones, well, of course we already have cosine, of these numbers, and then we'll actually be done. So now, let's just write the list out here. We have sine, cosine we already know, that's 8 over 17, good. Tangent we don't know, but it better be negative, right? So keep that in mind. Then to reciprocate these, we'll be getting cosecant, secant, and cotangent. Great. So now let's see if we can use this construction here to figure out what each of these are. So sine is opposite over hypotenuse, so that's going to be negative 15 over 17. And that makes sense because, again, sine is going to be negative in the fourth quadrant because only cosine is negative there. Great. Tangent. Tangent is, again, it's opposite over adjacent, so it's negative 15 over 8. Perfect. And then all of these are just the reciprocals of their counterparts. So this will be negative 17 over 15. This will be 17 over 8. And this finally will be negative 8 over 15. Awesome. And I'll box this all. Great. Now, we learned a lot in this section. There was a lot I discussed. So again, just like 6.2, I wouldn't doubt if a lot of you rewatch some of these ideas to get a better handle on how to apply these ideas to certain problems. There weren't too many crazy examples done, but the examples that I did, I think, showed the concept well. And that concludes 6.3. I'll see you in the next video for 6.4. It's going to be fun. See you then. Thanks for watching.